motion equation, there's a change in z over change in y equal to the negative acceleration in the y direction over g, which is gravity, plus acceleration in the z direction. For our use, we're only going to have the acceleration in the y over g. We will not have the acceleration in the z direction. For the first one we have no baffles, so there's a change in z and a change in y. And then for the second one we have one baffle. You can see that the change in z and a change in y were actually different from the first, and it's the same thing for the change in the z and a change in the y for two baffles. Alright, so let's assume we have a constant acceleration of 3 meters per second. From our equation before, we can find the acceleration over gravity will actually equal a negative 0.306. Alright, before we find our dz, we need to know our dy. So for our situation, we had a container that was 51 centimeters long. For no baffles, half of 51 centimeters is 25.5 centimeters. And with one baffle, we tried to put the baffle in the middle, so that would actually split the container in two separate halves. So half of 25.5 would actually be 12.75. And then for two baffles, we try to split the container up in thirds. So if you take 51 divided by 3 and then divided by 2, you will actually get 8.5 centimeters. So now if we plug everything into the equation for each situation, we can actually find dz. So for no baffles, we got 7.8 centimeters. For one baffle, we got 3.9 centimeters. And then for two baffles, we got 2.6 centimeters.
As seen in the picture, the materials included in this experiment were a fish tank, a pulley, C-clamps, rope, paperboard, duct tape, and a weight. This picture represents our experimental setup. The weight is tied to the rope, which is wrapped around the fish tank. The rope is through a pulley in order to reduce the friction when the weight is dropped. The weight is dropped off the edge of the table in order to create the acceleration needed for the experiment. In order to find the height of the water due to acceleration, a piece of duct tape was taped along the edge of the fish tank. This allowed the experimenters to place a mark wherever the water reached following the acceleration due to the weight. The baffles were configured in the fish tank as shown. The slow motion video demonstrates how the experiment will take place by releasing the weight off the table and allowing the fish tank to accelerate across the surface of the table. The purpose of the experiment is to determine the effect baffles have on the height the water reaches when there is a constant acceleration. As mentioned earlier, the experiment will include measurements from a tank with no baffles, one baffle, and two baffles. The height the water reaches under constant acceleration will be measured 4 times for each situation and averaged to determine the average height the water reaches in each trial. Through this, it can be determined whether or not baffles truly have an effect on the height the water reaches under constant acceleration. The full experimentation for one baffle and two baffles are shown throughout this video to give a good representation of the experimental process that was used. The average height the water reaches when no baffles are used was 6.1 centimeters. When only one baffle is used, the water reaches 5.1 centimeters, and when two baffles are used, the water reaches 4.3 centimeters. Therefore, it can be concluded that the more baffles that were used, the lower the height the water reached under constant acceleration. This is because as the dy decreases, dz in effect decreases as well. This was emphasized earlier in the video when discussing the theory behind linear acceleration. There were some possible sources of error that may have occurred during the experimentation process. There was some water in places along the table that was hard to dry up, which may have decreased the friction between the tank and the table. This in effect would increase the acceleration of the tank when the weight was released from the table. Hopefully, averaging the different trials diminished the effect of this source of error on the experimental process. It was also sometimes difficult to tell how high the water reached once acceleration took place. but again, averaging the 4 trials should decrease the effect the source of error had on the experiment. Although in the end the experimental process worked quite well and there was not many issues throughout the experimental process. Therefore, it can be concluded that the results are quite reliable. This slow motion video emphasizes the height the water reaches when no baffles are used. As you can see, the height of the water is over the tank and it takes quite a while for the water to actually settle down and return to steady state following the acceleration. This slow motion video emphasizes only one baffle being used within the fish tank. The water clearly does not reach the height that it did when no baffles are used. The water also takes less time to settle down to a steady state within the tank. This can be used as very useful qualitative information in real-life design work, and further supports the conclusions of this experiment that were reached. The final slow motion video demonstrates 2 baffles being used in order to decrease the height of the water within the tank when there is linear acceleration. Again, we see the water reaches an even lower level than one baffle and settles down faster to steady state than the other 2. This further reiterating the point that the more baffles that are used, the less the fluid within the tank will slosh around.
Baffles are used in several real-world applications. They're often used in the gas tanks of vehicles to prevent the flow of the fuel in the tank when it is under acceleration. The baffles reduce the overall height the gas rises to, and therefore the pressure being placed on the tank by the fluid. Baffles are often used in boats as well, like when they take on water for ballast. This allows the ballast water to remain spread out so that the weight of the water remains somewhat evenly distributed and does not cause the boat to capsize. Similarly, baffles are used to help regulate the flow of sound waves in large theaters or stadiums to help reduce crowd noise or help the audience use their seat at the performance. Baffles are a fairly simple idea and are very effective at regulating the flow of fluids.
Thanks for watching our video. Please hit the subscribe button.